Hello, Castle Hill scientists. I wanted to follow up with our Zoom meetings of Monday for the 5th graders and Tuesday for the 3rd and 4th graders, just to make sure that everybody understood what we did. And I also understand that some people didn't get the email about what was needed, and some people didn't even know we had our Zoom meeting. So I want to get everybody on the same page, go over the rocket building technique, and then talk a little bit more about the scientific method and the control versus variables. So first thing, you want to have your materials, my paper, scissors, straw, ruler, some kind of writing tool, and tape. And then later we're going to need a measuring tape to record the data when we start blowing off our rockets. So first I'm going to cut my body rocket out, which is 6 inches long by a width of 4 inches. And I'm going to make 3 of them. And right off the bat, I'm thinking about variables. So we need to make our first rocket with no changes whatsoever. So it's just going to be a normal 6 by 4 inch piece of paper. To the second one, I think I'm going to add some fins based on the observations I gather from my first attempt with control. And then my other variable, you can have many types of different variables, but one I'm going to use is having my rocket 7.5 inches long by 4 inches. So I'm going to go ahead and prepare these. So I'm going to wrap the paper around the straw, and I want to get it as tight as I can. In the beginning it's kind of hard, but eventually you can kind of soften up those paper molecules that are in there. It's kind of a physical change of matter, and I want to get it really, really tight. Okay, just so I know it's super, super snug. And then I'm going to release it just a little bit until the straw can slide. A little bit more until it pops out just like that. And then I'm going to take my tape. I should have prepared my pieces before. And I'm going to put 3 pieces of tape on my rocket. All right. A rocket's nothing more than a tube with a closed end and some type of energy so it can get the thrust it needs to get launched into the air. Think about that the next time you're in a plane. You're just in a tube and there's some energy that's hurling you through the sky. It's probably going to be much more aerodynamic than this little tube. So I've got my tube, and I'm going to close off one end simply by pressing the ends and putting some tape on the end. So there's my rocket, and we all know the energy for our rocket is going to be coming from our breath. I'm going to shoot this off about 5, 6, 7 times and make an observation. All right? Because we can't begin the scientific method until we've observed something. And then we can start asking questions, making a hypothesis, designing an experiment, running the experiment, collecting data, and then coming up with a conclusion. So give me a minute and I'm going to go see what I can observe. Here's the first one. Okay, so I'm done with my observations, and a couple things I noticed. That when I first shoot the rocket off, it goes nice and straight, but then it starts to get wobbly. All right, and when it does that, it's losing energy. It's wasting energy. It's not losing energy, it's wasting energy. Because our goal is to make this rocket go as far as possible. The other thing I noticed was the angle at which I was shooting it. Now, if I have it horizontal to the ground, gravity is going to pull it down. And if I have it going straight up too far, then it's going to waste a lot of energy going up and then falling down. So I want to have the right angle, and I found that an angle of about 45 degrees. So if we think of this as 0, we think of this as 90, 45 is right in the middle. Now that I've got my control, I can begin collecting data. Because when we're doing the scientific method, you have to have a control that you're going to use to compare everything else with. All right, if you have 10 different variables, you do one variable at a time and compare it to the control. For example, I've already put some fins on this one. This will be my first variable. I'm going to shoot this off 10 times, measure the distance. I'll shoot this one off 10 times, measure the distance. Then we can compare to see what did the fins do to either help or hinder the flight of the rocket. So I'm going to start collecting data. Okay, I've set up my little experiment area. I've got my measuring tape here, which I don't actually have a measuring tape. I just use a string and I measured out 1 foot intervals. And my launch start is going to be back by the whiteboard. And I'm going to shoot this direction 10 times and I'm going to see what the data says. But before that, the amazing thing about being in a science classroom is that you get to see really cool things that aren't even part of what we're doing. So I just happened to come over here and look at one of my cockroaches is molting. So the exoskeleton on this little fella, he's pushing himself out of it. Come on. There we go. So he's going to wiggle his way out, or she, and in a little bit will turn brown again. Kind of cool. And then we got Smitty just hanging out. All right, so I'm going to start my experiment, come back to you with the data. "14 and a half feet. Got 9 more to go." Okay, I have collected my data from my control and ran 10 trials. Each blast off is 1 trial, and it was pretty consistent except for this one right here, this 8. I realized that my ceiling is kind of low and I hit the ceiling a couple of times, so hopefully you guys will have a bigger ceiling at home, or else those are some of the things you need to accommodate for when you're doing an experiment. If you can minimize the variables, that's the goal. Okay, so I came up with an average of 14.65. That's just the plain old control. Now I'm going to put my fins on, and just a quick review to help for those who might need it. To make the fins, I got a rectangle. It's about 2 inches by 1.25 inches, something like that. And you can make your fins as big or small as you like. And I'm going to take that and fold it in half. And I'm going to cut at a diagonal. And then I'm going to snip the top off to make space for the tape. Then I'm going to take my tape, pull off enough so that it's going to cover the entire length, and put that right in the middle. I know it's kind of hard to see clear cellophane tape, and then I've got my control, which I'm going to set to the side. I made another one just like the control, and I'm going to put the tape and the fins right on the rocket. I want the tape to go down to the bottom, but I don't want to cover up the hole. So that last bit of tape is just there on the bottom. And put that in place. Okay, so there is how it looks initially. And then I can just fold it back so that they're standing out away from the rocket, like normal fins do. So I'm gonna make my second one, and then we're gonna do some more trials. Ready for blast off. Okay, trial number 2. I've got my fins on. See how this goes. It's about 15, 16 feet. Okay, got 9 more to go. Okay, so I've collected all my data for the one with the fins, and it's looking like this. 16, 20, 22, 21, 19. So the fins definitely make a big difference. That is a significant difference. The average came out to be 20.3, which is about 5 feet farther than the control. So aerodynamics does work. Now I'm going to shoot off my 7.5 inch rocket with no fins and see how that works. And here comes 7.5 no fins. Whoa. That like went curved way to the side. I have my data for the 7.5 inch rocket, and it was very interesting. I learned something more about aerodynamics and the importance of fins, because the 7.5 with no fins was kind of jumped all over the place. I had 16, 13, 15, 12, and what I noticed is the longer tube was very unstable. Like for this one at 12, it went straight and then hooked to the right. So fins are definitely a key factor in having things fly straight. We might have been able to guess that, but it's nice to have the data to back it up. And that's what science is all about. That is basically our experiment, but there's so much more you can do with this. And I want to give you a couple of ideas for different variables. One is that you can make a little cone, and for that all I did was cut a circle just like that, put a little snip in it, fold it, kind of twist it around on itself, kind of making like an oriental hat, and then putting some tape on it. Now, the tricky part is getting it onto your rocket. And for that, probably what you're going to need to do is get something where you can put your cone, take a dab of glue, plop it in the middle, and put your rocket in. Might need to find some place to keep it stable. But anyways, and some way that you can keep it upright while it dries. Okay. Another idea is to put a really long fin on it. And for this, it's pretty easy. All I did was cut a long triangle, and here's a second one. And I laid it down on my table and put the fin onto the rocket tube, took a length of tape, and I taped it in place. to make sure it's straight, just like that. Okay, well, so now this is kind of, it's like, well, wait a minute, that's not really a fin, it's just flat. So that's where we go to the opposite side. I'm going to put another piece of tape on it so it stands out from the rocket. All right, so it's looking like that. So this is another variable, so you can compare fin sizes. I've got these big ones, I got the smaller ones. There's so much more you can do with it. So have fun, everybody, and think of some new variables, and I look forward to hearing what you all come up with tomorrow for the 5th graders and on Friday for the 3rd and 4th. Take care. Bye-bye.